formal solution of the problem without giving any reference to whatever the potential is. And IR had shown an explicit integration of one of the potential, namely the inverse square law force, and that is basically what is called a Kepler's problem. So Kepler's problem is of -1 over r. So let me continue with the classification of orbits. We have this equation that energy at half mr dot square plus V effective of r is equal to energy. Or in other words, r dot square is equal to twice by m times E minus Vf.
Is able to reduce.
Yeah, I will interchangeably use reduced mass on the mass. The discussion on two-body problem was only to say that if you have two bodies, you put wherever m is there mu. Otherwise, we are talking about central force function. Okay, whenever you have two bodies, you put mu. Now we have V effective of R as V of R plus L squared divided by twice m R squared. The following analysis I will do with a particular choice of V of R, but conclusions I claim are more general than the particular choice that I have to choose. So let me choose V of R to be equal to minus K by R. This is the potential which Naina has used in the fourth session. This corresponds to an inverse square law force, like gravitation. Then I have this effective potential is equal to minus K is a positive constant, so minus K by R plus L square divided by 2m r. Now notice that this effective potential, when I draw this effective potential, this is the direction along which R increases, and if I have the potential which is equal to minus K by R, it will go to infinity as R goes to 0, it goes to 0 from negative side and R goes to infinity because what is given here is minus K. So this is the minus K. On the other hand, this one will go like this. So this is L square by 2m r square. this part. Now what I require here is the sum of these two. The effective potential will be like this. So this one we can add some color. There are color charts here. So let's say this is 1 over R potential. And this is 1 by L square by twice M square. And the effective potential we call it we can write this one as V effective R and this as minus K by R and this is L square. Now notice that if we consider, remember, if you have got what are the things that we can choose, as we have said in the morning, you can choose E, L, R0 and theta 0. These are the quantities that can be chosen to describe the motion. You understand the dynamics. If I choose, so these are arbitrary because these are along the path. I could have chosen at time t equal to 0 wherever I am in the path. So for any given L greater than 0, the choice reduces to the energy. So we can choose E differently to obtain different types of particles. We have to take different types of particles. Let's look at some characteristic values of E. Suppose if I take L is equal to 0, then this whole thing is upset. There is only an attractive force and everything will fall to the center of the force. So there is not much of interesting dynamics there. Correct? So if I have minus K by R and no angular momentum, then it will slowly come and fall in the center. So if L is greater than 0, then you have this term, and then there is a competition between these two, and we have some richness in the dynamics. So first let us consider the case where the energy is positive. So in case 1, we take energy greater than 0. That means we are considering some particular value here. So let me draw this as my total. Energy is going to be constant. So this is my energy E1. Okay, what the particle sees is an effective potential. So please look at only the blue color, the effective potential. Now you can see that if you look at this region, okay, so let me call this particular point where the energy is equal to effective potential. This point, let me call it as R0. Okay? Notice that if R is less than R0, then what happens? R is less than R0, V effective is more than E. Correct? V effective of R is more than E1. Correct? Now you look at this expression. If V effective is more than E1, then R dot square is negative. Correct? This implies R dot square is negative, which implies R dot is imaginary. Okay? So this is unphysical. Which essentially means that such a dynamics never takes place. So R cannot take values less than R0. And there is, if R is greater than R0, there is no restriction. Because for all values of R0 to infinity, energy is more than V effective, and hence R dot square is positive. Such velocity is not possible.
Practically, what does it mean? As a particle, I'm going to throw the particle.
Correct.
So I can do whatever I like.
Yeah, you can throw, but if there is a center, if there is a central force center, there is a minimum distance beyond which it cannot go near. Whether it is an attractive force or a repulsive force, it doesn't matter. Okay? So R can go to infinity.
Okay.
So R can go to infinity, but it cannot go beyond a minimum distance.
That distance, that total energy is not possible.
That is for a given angular momentum, right?
For a given angular.
If you take angular momentum to 0, then it's
Yeah, if we take LH to 0, then it can go and fall at the center. Okay, so this is for any given L greater than 0. All this discussion is for a positive L. So, which means, so how the trajectory will be for this kind of situation. So suppose if this is the force center, okay, let's say this is the center of force, then some particle can come from infinity and then can go up to infinity. This distance, this is called the distance of closest approach to the center of force, is R0. This distance is R0. And this orbit is a hyperbola. Okay, the orbit is a hyperbola. So you can see that if it is an attractive force, this is what happens. Okay? Even if it is a repulsive force, then it will come like this and then go off like this. But the closest approach can still be understood as existing.
So is this what they call a slingshot? And some of these space probe, they just take a small curve around the planet. So the space probe, they say some slingshot just loops around the planet. Is it like that?
I do not know whether that is, but usually this comet motion
Yeah, comet also does that.
is related to this kind of an orbit. But see, the point is, this is something which doesn't come back. It comes from somewhere, comes closest, and then goes on. So this is an unbounded orbit. Or these are called scattering orbits. Just scatters this way. Okay. Now in case 2 actually doesn't change much, because case 2 is if E1 is equal to 0. That means if it is like this, then also similar orbit will be there, but for reasons which are like what I not talked this morning, this will not be a hyperbola, but that will be a parabola. But that also is an unbounded orbit, and it will have a similar thing. So I will not discuss much. So case 2 is E2 is equal to 0. So we have parabola. And these two orbits are unbounded.
This will happen I think when you do the escape velocity.
Huh?
I think when you do the escape velocity, it will be levels. Because when you give escape velocity, the total energy is 0.
Yeah, even see escape velocity, you can have a bounded motion. You can put it in an orbit and then you can still have a bounded motion. Correct? But this is something there is no boundedness. It just comes from infinity, goes up to infinity. Huh? Coming closer than R is unphysical. It doesn't come. But anything at R it can come. Right? So up to that it is allowed. But below R not it cannot. That means huh? If it is, this is whatever I have drawn is attractive. Yeah, because it has angular momentum, right? So it has an angular momentum. If there is no angular momentum, it will come and fall into that. But because it has an angular momentum, it cannot come close. That is this value. This side of this force is because of the centrifugal value. So it will not allow that. See, when R is very small, 1 by R square will dominate over 1 by R. So repulsion dominates. So it will, even though force is attractive, when it is very close to R, it is a centrifugal force which will try to push it away. So that is why that is more dominant. Now case 3 is E is less than E3, which I will call it as less than. That means I am talking about some force, some energy, which is somewhere here. So I will call this as E2 is exactly 0. So this is E2. Now, interestingly, at this point, you have 2 points. That is, this point, which I will call it as R1, and this point, which I will call it as R2. And if your R is less than R1, V effective is more than E2. If R is greater than R2, then also V effective is more than E2. So the motion below R1 and above R2 is unphysical. Okay? Motion below R1 and above R2 is unphysical. What does it mean? It means that the movement is bounded above and bounded below. The radial coordinate cannot be more than R2, it cannot be less than R1. So you can imagine that you have these R1 and R2 are called turning points. So you can imagine you have got a circle of radius R1 and you have got another circle of radius R2, and the motion is bounded in this region. Correct? It can be any type of motion, but it is bounded. Okay, so you can have a motion like this. Like this. Okay, it can go like this. Okay, so motion is bounded. It's bounded. But not necessarily closed. That means it is not necessary that it should close onto itself. Bounded but not necessarily closed.
But sir, I read that the inverse square law that gravity must be a conic. This may not be conic.
You need not be also conic.
Oh, not necessarily.
See, inverse square law is a special case, but I am saying that this is, right now I have drawn inverse square law potential, but the conclusions are general for a large class of potentials. Okay, so in general, okay, this for an inverse square law it's a conic, but it's not necessary for arbitrary potential. But this classification is fairly general for a large class of potential. I will also tell you for what kind of potential this is general. And this argument is more general than the conclusions. The line of argument is more general. Now, in the fourth case, let me call an energy E4 which is equal to the minimum of this effective potential. What happens in that case? This lower limit, lower bound and upper bound will coincide. So what happens? The dynamics will confine to circle. Correct? So we have, that is, E4 is equal to V effective of R0. Okay, so in this case I am calling this as my R. Maybe I will call this as RL. Okay. And R0, where E by dr of V effective of R evaluated at R is equal to R0. That defines the minimum of the effective potential. Then we have circular arc. That is R1 and R2 coincide.
Can you think of cases in which V effective was more than one minimum?
V effective
So any minima.
Not as far as power law potentials are concerned. Maybe you can always look up.
Only the power law. Say 1 by r square, 1 by r raised to power. A by r square plus b by r raised to power.
Yeah.
Such cases you can have more.
Maybe it is possible. But if they are, let me see, the thing is, even if you have 1 by r square and 1 by r cube, yeah, more than one extrema is definitely possible. Maybe one is a maximum and the other is a minimum.
So we have as per, 2 or 3 minimum.
It's possible to construct some central potential for which you have more than one minimum. Okay, so what's your question? In case of
So
such,
in that case, this it may not be circular. For one of the minimum, this condition may be satisfied. For the other minimum, there will be a break.
yeah, depending on, so at that time, the dynamics will depend upon what is R0 and theta 0 that you have. Okay, so now this classification of orbits into unbounded orbits, bounded orbits, and circular orbits. Okay, as of now, I am not calling which is hyperbola, parabola, etc. So there are 3 classes. One is unbounded, or scattering orbits. Second, bounded orbits. And third, circular. And this will happen for energy greater than or equal to 0. This will happen for energy less than or equal to 0. And this will happen for energy is equal to V effective of R naught. That is minimum of V effective.
What happens if it is G5 less than V4?
That is unphysical again. Because if E is less than E4, for all R, V effective is more than E. Correct? Suppose if I take some E here, for every R, V effective is more than, so for all R, R naught is less than, R naught square is less than.
Again, in the case, you should continuity is almost 0 and you are very close to the origin. So you can have any active, any energy is physical.
Yeah, so if you are, that is,
Then angular momentum maybe have to be reduced. That's all.
angular momentum is,
Since less.
yeah, it's going to be very small. So if you are, that is what I am saying is
But you can choose a different angular momentum.
a different angular momentum. So you will come closer to that circular orbit. Now this classification is, we have obtained this classification by using minus k by r potential. But this is fairly general for any potential which has the following behavior. For example, so this classification of orbits, so obtained by using V of r is equal to minus Q by r. It is general for any central potential V of r that goes to first infinity that goes to infinity so I must have V effective in this form. That means what? This has to dominate, centrifugal force has to dominate as r goes to 0. Correct? So that means my potential must go to 0 much slower than 1 over r square. So V of r that goes to infinity slower than 1 over r square as r tends to 0 and goes to 0. So it goes to 0. Okay. It should also go to 0 slower than 1 over r square. Then this will become dominant as okay. So that goes to 0 slower than 1 over r square as r tends to infinity. So you have any potential which has these two properties. This classification of orbits is valid. Essentially, this means that the effective potential should be like this. That's all. If the effective potential is like this, you have these three choices of energies: positive energy, the bounded, unbounded orbits, bounded orbits, and circular orbits. But if you are not satisfying these two conditions, then this classification of unbounded, bounded, and circular orbits is not valid. Slower. Both are slower.
So slower than 1 by r square doesn't mean that it is some other 1 by r cube or something like that.
1 by r cube is faster.
Faster. So 1 by r can be
So 1 by, if you want to only power law, if you take 1 by r power alpha, alpha should be less than 2. Correct? That is why. See, the point is like this. If this goes slower to infinity, this term will dominate. If this goes slower to 0, then this term will dominate. So I want my potential to dominate as r goes to infinity, centrifugal term to dominate as r goes to 0. And that is possible. See, if it goes faster to 0, then the previous term only will dominate, right? I want this term to dominate. So it should go slower to 0, slower to infinity.
Is it sufficient goes to 0 going to infinity?
Goes to.
If it goes to 0 or tension is 0, slower or faster, still the effect is same, right?
No.
If it goes to 0?
No, suppose if it goes faster,
Yeah.
then this term only will dominate.
It will dominate, but eventually it will
It will go to 0 from the positive side, not from the negative
Yeah,
side.
what's wrong with that?
Then this classification is not true.
What goes wrong?
Let me show you. For example, if you take, so take this example. So let's say your V of r is minus k by r cube. Minus k by r, which goes to 0 faster than, it goes to 0 faster than 1 by r square, and it goes to infinity also faster than 1 by r square. So what happens in this case? So let me draw this picture, a similar picture here. So this term is as such, centrifugal term, and we have this term, it goes to infinity and goes to 0 faster than this term. As a result, what happens to this blue dye, this will dominate at infinity and this will dominate at 0. So the effective potential will be something like this. Effective potential will be something like this. Okay, there is no problem.
Where do you
See, this goes to 0 faster, so this is what remains. Correct? So this will dominate at r tends to infinity and this will dominate at r tends to 0.
But you have minimum, no?
No, some minimum is possible in this case. You look at minus 1 by r cubed plus 1 by r square. It's only a maximum. So this is going to be your B effect. This is L square by 2m r square, and this is minus k by r cubed, and this blue is B effect. But this method of classifying orbits I can still use, but the orbits will not be same. Correct? For example, if I ask what happens for an energy here, okay, if I have some energy here, okay, let me look at an energy here. Then what happens? There is a turning point here R1 and there is a turning point here R2. But what kind of turning point is this? Between R1 and R2, the motion is unphysical. So if it is less than R1, then it is fine. It will be forced towards the center of the force. If it is more than R2, it just goes up to infinity. But there is no motion between R1 and R2. Correct? This also has a circular orbit. That means if I have energy equal to the maximum of this effective potential, then these two will coincide and I have a circular orbit. So this is the circular orbit. Now this one, I have an R1 here and I have an R2 here. Okay? And this is forbidden. So if I give a radial R0 which is more than this, then what happens? For a given angular momentum, for a given energy like this, okay, so what happens? It will just come from somewhere and then escape like this. If I give something below this, what happens? Something below this, it just crosses into this. Okay? Just cross into this. Okay? This may not be true exactly, it may draw into this like this also. Anyway, eventually it will go to the center of this.
You can say eventually it goes because it's a conservative system, so just keep moving. It cannot cannot become dead. It cannot go in the center. Just keep moving. It's a conservative system. It may go to the center and bounce back.
Yeah, so it will be, let me say like that, so it will be a bounded motion inside. Okay, so this is a bounded motion inside, so it may go like this, and then I don't know how it will be, but we have to see for a given potential what kind of, but it will be bounded within that. There is an upper bound, but there is no lower bound.
So how can that be circular orbit when E is greater than?
Here?
Will it be bounded motion then?
Yeah, so the point is that now these two will coincide, but if I am able to give an exact initial condition on that circular orbit, it will be a circular orbit.
We are stable.
It's an unstable circular orbit, so it is very difficult to realize that one experimentally, because infinitesimally away from that will take you out that reality. So it is an unstable circular orbit, whereas in the previous case what we had was a stable circular orbit. So only if you are on that circle, you will be on that circle. It's a closed orbit, bounded orbit, closed orbit, but only an unstable bounded orbit, because it can just throw away if you are slightly away from the circle.
But stability is possible only in some reduced predication, like that's what Bertrand's theorem says, right?
Which is possible.
There's something called Bertrand's theorem, right?
Correct.
It says that only for one, either for Coulomb potential or for some harmonic potential, stable post orbit surface.
Yeah, Bertrand theorem says that we said we have this classification that unbounded orbits, bounded orbits, circular orbits. Now, if you ask a question, for what potentials all bounded orbits are closed? All bounded orbits need not be closed, right? So you ask a question, for what kind of potentials bounded orbits are always closed? So Bertrand theorem says there are only two such potentials. One is Coulomb potential, other is harmonic oscillator potential. Only for these two potentials, bounded orbits are closed, independent of what is the energy. But there is a large class of potentials for which, close to the circularity condition, if you are here, increase the energy slightly, you will get a bounded orbit that is closed. But for harmonic oscillator potential and Coulomb potential, it's not necessarily infinitesimally from this energy. Whatever is the energy, bounded orbits are closed. That is Bertrand's theorem. Okay. So as I said, that this method of classification, is quite general. We can use even for this kind of potential, which is not same as this. But if you have a potential which satisfies these two conditions, this classification is valid. But this does not satisfy these two conditions. So method of classification is okay, but this classification is not valid. Okay. So this is about the classification of orbits. And this is in general true for a large class of potentials, and this classification. Okay, suppose if I have an energy here, then what happens? So you can have an R here, or L, or whatever we call. So if R is less than this, what happens? If R is less than this, energy is more than Vf. That is fine. But if R is more than this, V effective is more than energy. So R cannot be more than that at all. Correct? No R more than that is possible. So it is again a bounded system. You have a circle of radius RL, and inside that the motion is bounded, and it cannot. There is like a infinite barrier. Okay. So this is the classification of this orbits.